Welcome to Mathematical Analysis. Today, we are going to explore one of the most powerful tools in mathematics, Maclaurin series expansions. Imagine you are a sculptor trying to create a perfect replica of a complex curved statue, but you are only allowed to use straight lines and simple parabolas. How would you do it? You would match the height, then the tilt, then the curvature, step by step. This is exactly what a Maclaurin series does to a complicated function. It builds a perfect replica using only simple polynomial terms. Let us dive in and see how this beautiful mathematical engine works. Now that we understand the sculptor analogy, let us look at the mathematical definition. A Maclaurin series is a specific tool that translates complicated non-algebraic functions like trigonometric waves or logarithms into an infinitely long polynomial. Why does this matter? Because computers and calculators cannot naturally compute a sine or a cosine. They only know how to add and multiply. By evaluating the original function and all of its rates of change or derivatives at the specific point where the input is 0, we can find the exact coefficients needed for our polynomial. It is actually a special case of a Taylor series, but anchoring it strictly at 0 makes the math much simpler and incredibly efficient for real-world computation. This concept leads us directly to the official Maclaurin series formula, which acts as a universal translation template. Conceptually, this formula comes from assuming a function can be written as a polynomial and then systematically matching its derivatives at the origin. Let us look at the symbols. The term f of x is the function we want to replicate. On the right, f0 is the starting height. The symbol f with a superscript n in parenthesis, evaluated at 0, represents the nth derivative of the function at the origin. Finally, n exclamation mark is n factorial, which is the product of all positive integers up to n. As the power of x increases, the factorial in the denominator grows incredibly fast. This ensures that the higher order terms become very small, keeping the infinite sum manageable and accurate. Before we move on to proving why this formula works, let us see this with a concrete example. We are given the trigonometric function cosine of x, and we are asked to find its Maclaurin series expansion. We chose this formula because we need to express cosine as a polynomial centered at 0. Our first step is to evaluate the original function at 0, which gives us exactly 1. This means our polynomial starts with a height of 1 on the y-axis. Next, we find the slope by taking the first derivative of cosine, which is negative sine. Evaluating negative sine at 0 gives us exactly 0. This tells us that the slope of the cosine wave at the origin is perfectly flat and the x term will completely disappear from our series. Continuing with our example, we now must find the curvature by taking the second derivative. The derivative of negative sine gives us negative cosine. When we evaluate this at 0, we get a value of negative 1. This means the curve bends downwards like a frown at the origin. If we keep going, the third derivative is positive sine, which evaluates to 0, wiping out the x cubed term. The fourth derivative brings us back to positive cosine, which evaluates to positive 1. We can clearly see a pattern emerging. The values at 0 repeat endlessly in a cycle of 1, 0, negative 1, 0. This predictable cycle is exactly what allows us to build the infinite series without calculating every single derivative manually. Now that we have our repeating pattern, let us plug these evaluated numbers directly into the general Maclaurin formula. We substitute 1, 0, negative 1 and 0 into the numerators. The terms with 0 completely vanish. This leaves us with our final answer. Notice that the final series only contains even powers of x. This makes perfect physical sense because cosine is an even function, meaning its graph is perfectly symmetrical across the vertical axis. The radius of convergence for this specific series is infinite, which means this polynomial will correctly calculate the cosine of x for literally any real number you plug in, no matter how large. Let us look at what we just built visually. In this diagram, the thick black wave is the exact cosine function. The horizontal axis represents the input angle in radians, and the vertical axis is the output value. The red curve is our second-degree approximation, a simple downward-facing parabola. Notice how perfectly it matches the black wave right at the origin, but it quickly falls away as you move left or right. The blue curve is the fourth-degree approximation, and the green curve is the sixth degree. You can clearly see that as we add more terms from our Maclaurin series, the polynomial hugs the original cosine wave for a much wider range. This diagram beautifully illustrates how an infinite series eventually perfectly overlaps the entire function. Now that we have successfully used this formula to expand the cosine function, let us understand where it comes from. We are setting out to derive the Maclaurin series formula from scratch. We start with a simple intuition. We assume our mystery function can be written as a sum of unknown constants multiplied by increasing powers of x. Our goal is to unmask these hidden constants, a0, a1, a2, and so on. To find the very first constant a0, we simply plug in 0 for x. Every single term with an x in it completely vanishes, leaving only a0 behind. So a0 is just the function evaluated at 0. Next, we take the first derivative of our entire infinite polynomial. The constant a0 disappears and the powers of x shift down by 1. If we once again plug in 0 for x, all the remaining x terms vanish instantly, revealing that our second constant, a1, is exactly equal to the first derivative evaluated at 0. Continuing our derivation, we now have our first two building blocks securely in place. To find the next constant, a2, we must take the second derivative. Taking the derivative of our previous equation brings down the exponents once again according to the standard power rule. Plugging in 0 for x makes all the later terms vanish into nothingness. This leaves us with the second derivative at 0 being exactly equal to 2 times a2. To isolate a2 by itself, we simply divide both sides by 2. If we continue this exact same process for the third derivative, we will end up dividing by 3 times 2 times 1, which is 3 factorial. This reveals a beautiful, highly predictable pattern. Every single term's constant is the nth derivative evaluated at 0 divided by n factorial. We have now rigorously proven the universal template we used earlier. So we have proven that the Maclaurin formula holds. This brings us to a crucial limitation we must always check: the radius of convergence. This is the specific range of x values for which our infinite polynomial actually matches the original function. For some functions, like cosine, it works perfectly for any number. But for others, the polynomial goes completely crazy and produces garbage results if you stray too far from the center point of 0. However, if we only look at a very tiny window right around 0, we do not need an infinite number of terms. We can just chop off the series after the x squared term. This creates the famous small angle approximation for the cosine function. In physics and engineering, if the angle is very close to 0, the higher powers become so microscopically small that they simply do not matter, making impossible differential equations easily solvable. Before we move on to our final example, let us see how Maclaurin series handles a function that misbehaves. We are asked to find the expansion for the natural logarithm. We cannot expand log of x directly around 0 because the logarithm of 0 is undefined and shoots off to negative infinity. Instead, we shift the function to the left by expanding log of 1 plus x, which is perfectly well behaved at 0. The natural logarithm of 1 is exactly 0, so our polynomial will have no constant starting term. Next, we take the first derivative using the chain rule, which gives us 1 over 1 plus x. Evaluating this at 0 gives us exactly 1. We then take the second derivative by applying the power rule, bringing the negative 1 down to the front. Evaluating this at 0 gives us a value of -1, meaning the curve immediately starts bending downwards. Continuing with our logarithm example, we take the third derivative. The -2 exponent comes down and multiplies with the -1, giving us a +2. Evaluating this at 0 gives us +2. We now have enough terms to plug into our general Maclaurin formula. We must remember to divide each of these evaluated numbers by its corresponding factorial. This division causes interesting cancellations. The factorials in the denominator cancel out with the numbers generated by the derivatives, leaving just the plain integers in the denominators. This is our final series. Physically, unlike the cosine series, this formula has a strict interval of convergence between -1 and +1. If you try to plug in x equals 2, the terms will grow larger and larger, and the sum will explode to infinity. Now that we have seen trigonometric and logarithmic functions, let us look at a powerful algebraic generalization. We are asked to expand the function 1 plus x raised to the power of k, where k is any real number. This allows us to expand expressions raised to fractional or negative powers, which basic algebra cannot handle. We follow the exact same step-by-step derivative process. The function evaluated at 0 is simply 1 raised to the power of k, which is just 1. Next, we take the first derivative using the standard power rule, bringing the exponent k down to the front. Evaluating this at 0 leaves us with just the number k. We then take the second derivative by bringing down the new exponent, k minus 1, to multiply with the k already in front. Evaluating this at 0 gives us k multiplied by k minus 1. Continuing with our binomial expansion, we can now plug these evaluated derivatives directly into the standard Maclaurin formula. We place our values of 1, k, and k times k minus 1 into the numerators. And we must remember to include the factorials in the denominators as required by the template. This result is known as the binomial series. Physically, if k is a positive integer, the series eventually stops and gives you a finite polynomial. But if k is a fraction or a negative number, the series goes on forever into infinity, with a strict radius of convergence between -1 and +1. This specific expansion is heavily used in physics to create approximations for things like kinetic energy at speeds close to the speed of light. We have covered a lot of ground today, so let us reinforce the most important ideas. First, a Maclaurin series is a mathematical translation tool that converts complex, non-algebraic functions into infinite polynomials centered strictly at 0. Second, we build this perfect replica by matching the function's value and all its rates of change at the origin. Third, we must always respect the radius of convergence, which is the safe zone where our polynomial accurately matches the original curve. These series are the hidden engines inside almost every digital device you own, allowing computers to calculate sines, cosines, and logarithms using only basic arithmetic. You have now mastered a concept that beautifully bridges the gap between abstract calculus and practical real-world computation. Great work today.